rather straightforward physical principle, a principle that I'm sure we believe permeates many real-life situations. It's what I call the rule of compound interest. Namely, let's suppose we have a physical situation in which the quantity that we're measuring, which we'll call m, in other words, the rate of change of the quantity is proportional to the amount present. dm dt equals km. Now, notice that this is a pretty harmless statement. The rate of change is proportional to the amount present. We certainly would expect that many experiments would run this way, and there seems to be nothing at all supernatural about this kind of an assumption. At any rate, let's apply our previous principles and see if we can't, from this differential equation, figure out what m has to be. Separating the variables, we get that dm over m is equal to k dt, and now integrating, meaning taking the inverse derivative, we have what? That the integral of dm over m is equal to kt plus a constant. Now you see, the interesting point is, at this stage of the game, we do not know explicitly how to find a function whose derivative with respect to m is 1 over m. In fact, that's the problem that underlies today's lecture. And we will try to answer this question, showing how once we tackle this from a philosophic point of view, the rest of the details follow from material that we've already learned. At any rate, focusing our attention on the problem, the question is this: to determine a function which I'll call capital L of x, the L sort of to forewarn us of the fact that we will somehow get a logarithm out of this, such that L prime of x is 1 over x. And you see, what I want you to notice is that if you write 1 over x in exponential form, in other words, if you try to write 1 over x as x to the n, notice that to solve this problem, L of x would be what? The integral of x to the minus 1 dx. In other words, this is the case of integral x to the n dx with n equal to minus 1. And you'll recall that when we studied the recipe, let me just write that over here, when we studied the recipe of how you integrate x to the n, we saw that that was x to the n plus 1 over n plus 1 plus a constant, and we then observed that this doesn't even make sense when n is equal to minus 1, because we'd have a 0 denominator. From another point of view, the way to look at this is we said what? That when you differentiate, you lower the exponent by 1. Notice that to wind up with an exponent of minus 1, we would have had to start with an exponent of 0. But when you differentiate x to the 0, that being a constant, the derivative of x to the 0 is 0. It's not 1 over x. You see, in other words, this particular recipe that we were talking about, we don't have working for us. In other words, this is an interesting point again. You say, gee whiz, if the recipe for integral x to the n dx works for everything except n equals minus 1, nothing's perfect, let's be content. Since it works for every number except that one, why worry? This is analogous to when we talked about taking derivatives and saw that we get a 0 over 0 form every time. You see, if you pick a function at random, the likelihood that the limit of f of x as x approaches a, the likelihood of that being 0 over 0 is very small, except when you form the derivative, you always get 0 over 0. And in a similar way, granted that integral x to the minus 1 dx is one very special case, what we have seen is that this comes up every single time that we want to solve a problem of the form dm dt equals km. In other words, then, what it really boils down to is that unless we can come up with a function L of x whose derivative is 1 over x, we cannot solve the problem that we started off today's lesson with. In other words, we must leave it in the form integral dm over m equals